Okay. So how many of you know what an exoplanet is? I guess everybody knows. That's pretty cool. Because I did not know when I joined NASA like 3 years ago. I had an idea, but I did not really know what an exoplanet is. There is a very specific definition of an exoplanet, which relates to what's the density, how far it is, how big the star it's revolving around. But I mean, for this talk, let's just assume anything which is not a star and going around a star is an exoplanet. Okay, I think you're showing my emails. That is not a good thing to do. Yeah, I don't know. I can probably get screwed up for that. No, my wife is there. That's even worse. Okay, so I guess now I can start. This works. Okay, so my topic for today is mission concept for multi-pixel imaging of exoplanet. Blah blah blah. It's a big topic, but the whole point is we're going to the interstellar medium. We have a mission which we want to take between, say, where the Pluto starts, Pluto orbits ends, and then the other star infant starts. So, but before I start, I just wanted to give an overview where I work. This is where I work. This is JPL. How many of you have been there for open houses? Okay, so you all know it's a cool place. So before I go into too much, he gave a bio for me, but I just wanted to introduce myself. I'm a 32 years old from India. Just got married one month ago. I grew up loving Star Trek. I did Bachelors in Civil Engineering from India. I did not care about civil engineering at all. Just did it for no reason, and then I realized this was a waste of time. Came to the US when everything was easy. It was easier to come here. I came here, did some masters at Aerospace Engineering at Georgia Tech, did a Ph.D. at Georgia Tech, and started playing squash. I did a lot of squash when I was here. I'm getting into martial arts thanks to Loic, my friend. And I've been at NASA for 3 years. I've been designing future space missions. It's more like a hobby, not like a work. I look up to going to work every day and try not to come back early. So it's sort of fun, but it also requires you to think a little bit out of the box. And that's one thing which JPL excels in compared to other places. I have friends who work where we don't have a single mindset of how to solve a problem. We look at a problem from a multitude of perspectives. We also have artists. We have people who have background from places like economy and hardware in automotive industry. So they come up with different kind of solutions to the problems which we don't know even exist. So anyhow, so now we can actually start. So what's the first thing which comes to you guys' mind when you think about space? What's the first question? What do you think? Anybody? Emptiness? Anybody from here? Cold. Aliens. There you go. So that's close enough. That's what I thought. So when I was small, I should always think this question: are we alone? Right? That's the first question we always think about when we look at space or when we look upwards. And to give an idea, this is our Milky Way galaxy. You've seen this poster on your Apple laptops or some MacBook, but you never realize that this tiny dot on the left, that's a solar system. And it's so small, and that's just 1 pixel. And the whole solar system is so huge, it took a spacecraft 10 years to reach Pluto from Earth. So imagine going from this dot to this dot, it takes hundreds of millions of years. So how would he even figure out where this guy lies? So an alien, if you want to look for life, probably want to look at an exoplanet. See, that's how and why we actually look at exoplanets. So now the second question is, what happened recently was NASA launched a bunch of missions from Hubble, Spitzer, Kepler, TESS, JWST, and that started a big discovery path for discovering exoplanets. As you can see, we started discovering the first exoplanet in 1998. In 2016, everything just shot up because we found a new way of doing it. And that just immediately opened the whole field of exoplanet imaging. And another interesting fact which some of you might not know, I did not know this long time back. When you look at an exoplanet, you're also looking back in time because of Einstein. He said it's probably true. So, but it turns out to be an important factor. If you look at exoplanets which are very far away, you're looking back in time and you might not get the right information. So it's crucial to find an exoplanet which is close enough to you, not just an exoplanet. So that makes it even harder, because it's very hard to get the right alignment for this, for galaxies which are close enough for your telescopes. So, and recently, well, last month, we discovered 7 Earth-like exoplanets, and 3 of them are potentially habitable. So you can see how this field is accelerating. So there's a huge, influx of discovery which is going on right now. And there are 3 different methods of detecting an exoplanet, basically. The first one is called direct imaging, which is how the name says. You image the exoplanet. Probably it's very faint, it's very far, so you need a chronograph. That's why you see in these pictures, when you see from NASA or everywhere, you see this exoplanet, and this dot is actually the exoplanet, the small dot here. The thing in the middle, that's the sun or the star for that solar system. And you don't see it because the chronograph is hiding it away. The second method, which was recently discovered approximately 10 years ago when we had good and sensitive instruments, called astrometry. You basically see the orbit of the parent sun or the parent star and see the wobbles in its orbit. From there, you can deduce what kind of planets are going around it, because their gravity will have the effect on the parent star. This works nicely if the exoplanet is big. If you have an exoplanet the size of Earth, it's very hard to see that wobble if it's billions of light years away. So recently, we got this new technology, and the Kepler spacecraft, we found this new method called the transit method. It sounds pretty simple now, but we didn't have the right technology to detect this kind of signals before. So when a small planet passes through in front of a big star, you get a dip in the light which gets emitted from there, and that dip is recorded. And from the dip, you can get a lot of information, like what the planet is made of, how far is it, how big it is, and what's the density, and what's the star made of. So this is the real kicker, which got all these discoveries suddenly showing up in the last few years. It's because of this method, which was discovered. So, I mean, because we have been discovering so many of these planets, soon we will probably get this news. Earth 2.0 discovered. Like, oh, we found this new awesome planet which looks like a very good place to go. It might have an atmosphere. JWST, which is being launched in 2018, finally was supposed to be in 2010, but it got delayed. And that telescope is supposed to look at atmospheres of exoplanet and figure out if it has oxygen or other big compounds like carbon or methane. From there on, we can deduce how habitable they are. There's a good chance we might find a habitable planet in the next 5 years, a potentially highly habitable planet. And then the question will become, what do we do next? What's the next step? And that's what we're trying to answer in this mission concept. That's where all of this started from. So when I was hired at JPL, one of the high-up managers, he told me he wants to figure out how do we do the next step. And he didn't even know. He thought the next step is just to go there. It turns out going there is very hard. It takes millions of years. The next best thing is to image the exoplanet. But there was a big problem. The problem was, right now, we are here. This is our current capability. That's all we can see, a dot. That's not really called, it's good for the first level of exploration, but you can't answer questions like, well, there's life there, or well, there's something there to, which is very, interesting to see. So how do we go from there to here, which is almost a 1,000 by 1,000 pixel resolution image of an exoplanet? And this was a revolutionary, goal to shoot for. This is what we do at JPL. We do crazy things. So we wanted to achieve something like, how can we do this with the current capability, not waiting on next hundreds of years? And it turns out the answer actually comes from something called a solar gravity lens. I'll go into detail on what that is, but the timing is right for that kind of mission to occur. So Voyager and Kepler, Voyager was the spacecraft which was launched at JPL in 1970s. They did a bunch of flybys of Jupiter, Uranus, Neptune. They basically they were the first spacecraft to ever go to these moons, or these planets actually, sorry, and the moons, of course. And then they went into the interstellar medium. One of them went up from the plane of the solar system, one of them went below. And Voyager 1 is the fastest spacecraft we ever launched. It's right now at 140 AU, which is astronomical units from here. Earth is 1 AU. So just to give you a perspective, it takes a plane approximately 19 years to travel 1 AU, a normal commercial jet. So 140 AU is pretty far. It took like 40 years for Voyager to reach there. So now we said, well, they are nearing their life. They have lasted more than 45 years. They were not supposed to even last for 10 years. So what's the next step? And I think the time is right to take the next bold step, to take and image a big exoplanet, which will be found in the next 5 years, to see if you can find life there. And I know when I heard this first concept for the solar gravity lens from my fellow astrophysicists, who were the ones who discovered the physics behind the solar gravity lens, I was very, very confused. I was like, what the hell is solar gravity lens? I mean, sure, solar gravity lens, yeah, what does that even mean? I understand it was a lens, but I mean, what do you mean gravity? How can gravity be a lens? It turns out it's a nature's gift for us. It's not a focal point, it's a line at 550 AU from the sun. So what happens is the light from other planets, they go around the sun, and because Einstein was right, lights bend, and they create a line, and the sun becomes your focus. You're basically your mirror. It focuses the light at 550 AU, and it goes all the way to like thousands of AUs beyond that. So if you have a small telescope there, you can get a magnification factor of 1,000,000. So say you have a planet 1 million light years away somewhere. The light comes from there, gets focused at 550 AU from our sun, and we have a spacecraft there, a small 1 meter telescope. It can take 1,000 pixels resolution image, which we want to take. So now the challenge becomes, how do we reach that mark of 550 AU? It's pretty damn far. I mean, compared to Voyager, took 45 years to reach what, 140 AU, and Voyager was lucky; it had this planetary alignment to take advantage of, which was taking 3 gravity assists from Jupiter, Saturn, and Uranus, and that planetary alignment is not occurring until 200 years from now. So, well, we have to find a new way of getting spacecraft out there much faster than we ever done before. So, we need to go really quick. And just to give an idea, the JWST, the new telescope which is being launched, is a 6.4 meter big wide telescope. It costed $8.4 billion to build that telescope. It's being launched next year. Hopefully, it will work all fine. So, because we can't fix that one, we fixed Hubble because it was close to us. That one is going far away from us. So, to get an image of similar resolution, we need a 10-kilometer wide telescope in space near Earth. There is no way nobody will fund that. That's trillions of dollars. So the only way to get an image like that from an exoplanet is to go to the solar gravity lens. That's a nature's gift. We know we have to learn how to use it. And so that got everybody excited. Oh wow, there is this awesome point in space where we can go and use the sun as a lens. It's great. Let's do it. And then the work came down upon me and my team's head. Well, now how do we get there? How do we build a spacecraft which can even go there and do this whole big whole big campaign? So from there, just giving an idea where that lies, this is just a chart we created. This is a log scale. So it's showing how long the light takes to reach different points in space. And this is the ecliptic plane. So this is where the Voyager 1 spacecraft went above the plane, the Voyager 2 went below the plane, and this is where the solar gravity lens lies. It's approximately 500 AU. It takes light 3 days to reach there. So it's pretty far away. And also we knew a mission we'll send there won't reach there in like 5 years. It'll probably we wanted to send the mission there in less than 35 years. But nobody will fund a mission which takes 35 years to achieve any science, right? So the idea we had was there's a huge amount of science to be done in this area. And that is the interstellar medium, which is as we know it. And that's what we want to also explore as we go all the way to a final goal of solar gravity lens. And that's how we started working on the mission concept. So we defined these mission goals when we started the study. Well, we have to reach the 550 AU in 35 years because that's probably the life of one guy, a scientist who starts working on it. You don't want to work on it and you die and nothing happens. So that's how we actually came up with that number, 35 years. And we also need to reach a large Kuiper belt object in 11 years. So what is a Kuiper belt object? Pluto is a Kuiper belt object. And Pluto is not the biggest one. There are 5 more which are almost as big as Pluto, one of them bigger than Pluto, around 50 AU. So we want to have a mission which can reach that distance in less than 11 years, which was very challenging. Because that means you have to go really fast, almost 10 times faster than what we have ever done before, without the planetary alignment which Voyager's had. So, and that's shown here that we wanted to achieve speeds of 14 AU per year. So you're traveling 14 astronomical units per year when you're escaping the solar system. And we want to launch between next decade. We don't want to wait 2040 to launch this mission. Again, I would not be interested in working on it if that's the case. So, and then it has to use neutron technology. Any mission launched in 2025 has to have a technology cutoff at 2020. That's just how NASA works. They cut off the technology 5 years before the mission is launched because they don't want to keep on infusing new technology and creating risk in the mission. So, so that all enabled into a specific mission design space where we had to find a new way of doing this. So before I go into that, I just want to give a basics of what orbits are, just so that people understand a little bit what's going on. So say you have a small planet going around a bigger planet. This part is where the velocity is low. This part is where the velocity is large. That's all you need to understand. In a closed orbit, when the planet is closer to the bigger planet, you're going faster. It's because gravity pulling you faster. That's all it is. The second thing you should remember is you can go from a circular orbit to an elliptical orbit to an escape orbit. Escape orbit means you will never come back. You leave, you're done. And that's what we want to achieve. We want to escape from Earth, and then we want to escape from the moon and the sun. Sorry, not the moon. It's so much hard to escape from the sun because sun's gravity is huge. It has controlled all our planets for hundreds of millions of years. So we need to escape that. So we need to have an energy which can pull us away from the sun's energy. So it turns out to escape the sun, we have to go really close to the sun first. Really, really close. So if you do the math, it turns out if you do a big maneuver, you burn a lot of propellant and fire rockets very close to the sun, you get a huge jump in your increase in your energy. And that's because it's called the Oberth effect. It's something which is well known, used by all spacecrafts. When the spacecrafts come into, say, close to Saturn, they want to go into orbit around Saturn, they will fire the engines very close to Saturn or very close to Mars. They will not fire it far away from Mars. The closer you are to a gravity well, the more efficient your engine becomes. And sun is the biggest gravity well we ever know. So your efficiency of the engine goes up by thousands of percent. So with that, I will just want to show how this mission will happen. This is what I generally, my work is. So you will see here, you will see the spacecraft launching from Earth, doing a Venus flyby, and you will here on the top, you will see velocity changes, how the velocity is changing on the spacecraft. Here you're seeing a view on the plane from side view. So you see how out of plane and in plane is going. And this is from top, how it looks like. It's not very clear, but it'll probably get clear when I play it, I think. And I'll talk to it as I go. So you can see the spacecraft just launched. It did a Venus flyby. And you can see the velocity changed. Oh, shit. I'm sorry. That was a mistake by myself. Sorry. I'm not used to having like 3 pointers in front of me. Okay. All right. So you will see a big velocity change suddenly when it does a Venus flyby. It does a flyby, the velocity changed. And that's a small jump, it's significant. And now it's going out, away, it'll come back. It's again to the slowest point. You saw the ellipse before. This is the slowest point in its orbit. It's coming back again, close to its closest point to the sun. It's getting faster and faster. You can see the velocity increasing again, like we expect. Now I'll do another Earth flyby, the velocity will change. Again, so there's a small dip here. This small dip is the flyby of Earth. And that is enough to change your direction completely in space. Now it will go up way higher. This is probably beyond Mars. It will come back again, do another Earth flyby to make it even more energetic so that it can encounter Jupiter. It wants to go to Jupiter because Jupiter has enough energy to throw you all the way back to sun. You cannot go directly to the sun from Earth because Earth is going so faster on the sun, you have to slow down that energy first. And that is way higher than actually going to Jupiter and letting Jupiter throw you back. Because Jupiter is such a big, bulky planet, it can just throw you around anywhere you want. So you can see the spacecraft is going down, it will do another Earth flyby and it will go and fly to Jupiter. When it flies to Jupiter, Jupiter will do something crazy. Imagine a spacecraft coming like this towards you, and Jupiter just throws it down like that, completely down. And go completely out of plane, you will see it here, and then it will come and go very close to the sun, and then it will just shoot out of the solar system. So that's the basic how the mission will occur. And you'll see probably happening right now. So it's going close to Jupiter, and suddenly you will see it coming back immediately. This is not cartoon, this is actual simulations. So see, it just started coming back because Jupiter just threw it back all the way close to the sun. It's weird that you have to go all the way out to come back close to the sun, but that's how it is optimal. You can't just go close to the sun immediately. So you can see it actually going below the plane. It's a straight line going below the plane, and once it comes close to the sun, it will go at a speed of 300 kilometers per second. That's the fastest we would ever have gone. So see, now it's like just leaving, the speed has just increased dramatically. and you saw a huge spike. That was the close approach to the sun. The velocity just increased like crazy. And this is the first Kuiper Belt object it will visit in 9 years after launch. It's called Maki. It is the weirdest Kuiper Belt object we have ever seen. It is like a rugby ball, but two balls going around each other, somehow stable. We don't know why yet. We need to study that. And it might even have atmosphere, which we don't know yet about. So yeah, well, that looks like cool. That's kind of the job work I do all the time, figuring these paths out, doing Google Maps in space in a way. So, how the spacecraft looks like, generally you see these huge spacecraft being launched. The actual science is only done by 500 kilograms of spacecraft. Everything else is mostly fuel. Like the total launch mass is 11 tons. 9 tons is just fuel because we need to do that big burn close to the sun to make our exit. And it is launched on the world's biggest launch rocket, which will hopefully be built in the next 2 years if we don't get funding cuts from Congress. So, and this is how it fits inside the launch vehicle. See how big the launch vehicle is. And you will see these flat things in front of the spacecraft. This is because we're going close to the sun. We will fry if we don't have a shield. This is a heat shield. And we have 2 of them, the front one and the side one. And this is how they work. So when you're coming close to the sun, when you're at Mercury, you throw away your back structure and you expose your rocket nozzle. You start pointing towards the sun, your front shield, so that you don't get hot. Your heat shield gets really hot, but you don't want a spacecraft which is here in between to get hot. And once you're really close to the sun, you use a side shield. You go into the sideway position so that you can fire a rocket motor. You fire, and then you're out, and that's it. But that whole thing takes 10 minutes, and so it's super hard to track. It has to be automatically navigated. So we're developing this auto navigation technology at JPL right now for these kind of missions. But so this will be very cool. When this happens, it will be an amazing event, and you should be able to see it from Earth. In terms of you will get signals. You won't be able to see it because the spacecraft will be 3 solar radii from the sun. So it will be so close to the sun that the whole sky for the spacecraft is filled with sun. The sun will just completely obscure the spacecraft because of the glare. You won't be able to see it optically. So this is the timeline we are working towards right now. This is not in the congressional budget yet with this mission. It's just getting excited. So we're just getting people excited about it. So as we build more people, more support for it, people at Congress and headquarters will start noticing it more and more. So it's a next Voyager, like we say, and we want to launch it in sometime in mid-2020s, and we want it to do all kind of science starting 2030s. So that's the whole plan. And I also wanted to talk something more. One more slide, which is basically in my undergrad, I did some habitat work in space. I developed some habitat, and this talk is about living in space. So I worked with 2 more people. We developed Kalpana 1 space colony. This was just undergrad, so probably it had a bunch of mistakes in it, which I don't want to talk about. But a designer, he called me and he took our design and made these cool plots out of it, and it looks really nice. It looks actually something which you would want to live in, which we never thought. I just want to get a paper out. But one more thing I want to just let you guys know to inspire you. This is I don't know how many have you seen this picture. This is the pale blue dot picture. This was taken by Voyager. This is Earth, taken from Neptune. The small dot is Earth. And this was a new picture taken by our spacecraft, Cassini, in 2 years ago. And this is Earth, 1 small dot, 1.2 billion kilometers away. So, and that's how I want to end this talk. Just want to play this video from Carl Sagan, who was I'm a big fan of him. So, and after this, I'm done. So, oh, no video. I can't hear the sound. You wanna? Oh, yeah. Without that, you won't get sound. You wanna start? I'm sure some of you have seen this. It's a pale blue dot video.
Here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering. Thousands of confident religions, ideologies, and economic doctrines. Every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there on a mote of dust, suspended in a sunbeam. The Earth is a very small stage in a vast cosmic arena. Think of the rivers of blood spilled by all those generals and emperors, so that in glory and triumph they could become the momentary masters of a fraction of a dot. Think of the endless cruelties visited by the inhabitants of one corner of this pixel on the scarcely distinguishable inhabitants of some other corner. How frequent their misunderstandings, how eager they are to kill one another, how fervent their hatreds. Our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. The Earth is the only world known so far to harbor life. There is nowhere else, at least in the near future, to which our species could migrate. Visit? Yes. Settle? Not yet. Like it or not, for the moment, the Earth is where we make our stand. It has been said that astronomy is a humbling and character-building experience. There is perhaps no better demonstration of the folly of human conceits than this distant image. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known.
Yeah, perfect. Thank you.
If you guys have any questions for Nitin.
I should have asked that myself. If you guys have any questions, shoot away. Yep. Oh yeah, very good question. And I forgot to mention that. It uses radioisotope power. I don't know if this is working. Oh, it's working. It uses radioisotope power, which is basically the same used by the Mars Science Laboratory on Curiosity, same by Voyager, same by Cassini. We're getting short of plutonium, but there's still enough that this mission can use it. It only needs 2 of them. So, any other question? Yep.
Is there any plans for work on comets? Because I noticed that the orbit is sort of similar to how comets come in really close to the sun.
So, I mean, that's a good question. We haven't looked at visiting comets on the way, and I'm pretty sure there might be some of them which we can visit. We have to realize space is huge and vast. Unless we target it, we will not find it. So this is very early design phase of the mission, and we are starting a new phase in June, where we will look into more details on, well, can we add electric propulsion to it and make it better and faster? So all of that has to be done. So this is very early. So, but that's something which will be in mind for the scientists. The damn scientists want everything. They want to go everywhere in one mission. So we would have to stop them. So it'll come up. Any other question? All right, I think we're done. Thank you.